Hi everyone. Thank you for coming to this session. It's great to see so many of you here. So today we'll have Andy Turner from EPCC giving us a talk about OpenFabrics and UCX on ARCHER2. So Andy, take it away.
Hi, thanks Alexei. Thanks for coming along today. This presentation was originally written for the Cray User Group conference this year. But it seems to be probably of interest more widely to people who use ARCHER2 in particular, and potentially other Cray EX systems. So what we're hopefully looking at, or what we're going to talk about today, is the performance of two different routing protocols, or transport protocols that are used underneath MPI to send messages across the interconnect. I've got a few slides, first of all, to give some sort of introduction, but first we've got the obligatory sort of slides about reusing the material and the partners who make up the ARCHER2 service, who are all involved in delivering it, UKRI who pay for it, EPCC who run the service provision, that's sort of a general administration of the service, and also the CSE service, which is the bit which helps users optimize port their codes and get technical help on the system. University of Edinburgh provide the hosting and accommodation for the system, and HPE, who've developed the hardware and also provide some expertise, both in terms of running the hardware and in terms of helping users out on the system. So most people here probably are familiar with ARCHER2, so I'm going to go quite quickly through the introductory section, which is all about ARCHER2, the service and the system, and get on to the actual results from the work we did here, looking at the different transport layers, or the transport protocols. Sorry, I'll try and be consistent with terminology, but no doubt I will slip up at various points. ARCHER2, hopefully as you know, it is the latest the UK National Supercomputing Service. It's based around a very large CPU-based system. An HPE Cray EX system's got around 750,000 cores, and it's one of the largest CPU-based systems in the world at the moment. What we wanted to do here is, as part of the software available on the system, there are two different transport protocols that underlie MPI communications on the system. One of them is called, one of them is sort of labeled on the system as OFI, that's the OpenFabrics transport protocol, and the other one's the proprietary Mellanox UCX transport protocol. And both of these can be selected, or either of these can be selected at runtimes by users on the service, simply by changing a module on the system. You can just change the modules you've got loaded, and you don't need to recompile your code. It just switches the different transport protocol. So with that, it's quite easy to switch. What we wanted to do was, first of all, we'll have a look at if there was any performance difference between the two different transport protocols, and hopefully, using that information, provide some good advice to users on which protocol to choose and when. And maybe also understand some of the performance characteristics of the slingshot interconnect, which is the fabric that links together all the compute nodes and allows MPI communications to happen on the system, because it's a new technology underlying some of the largest systems in the world that has not had huge amounts of exposure yet. And also maybe identify some problems areas for improvement, particularly at for large scale MPI calculations. So in terms of ARCHER2 itself, as I said, it's the UK National Supercomputing Service. It covers a wide range of different research, from materials modeling and climate modeling and earth systems modeling, to engineering applications, more biomolecular applications, and various other bits and pieces. In terms of how this sense of scale, it's got about 3,000 users, although not all of those are active all of the time. And it's got a huge range of software that it's used for. It's a very general purpose system. So the top 10 codes make up about 50% of the utilization together. Top 40 codes around 75%, but then there's hundreds and hundreds of other codes. So obviously, with that broad base, the system has to be sort of generally usable, and it may be the case that something that works well for one code at one scale doesn't work well for one code at another scale. And it's impossible for us as the service to investigate the detailed performance characteristics of every code. But what we try to do is pick some applications, as you'll see later, that cover a range of different different application types and use cases on the system, and have various different characteristics of MPI communication types to try and get some sense of where the differences between the differing transport protocols lie. So the ARCHER2 system itself, mentioned it's very large, just over 750,000 compute nodes. It has the HPE Cray Slingshot 10 interconnect, which is a similar technology, but a little bit different from the interconnect that's in the new exascale system in the US, which is Slingshot 11. It's the next version. In terms of compute nodes, we have 2 AMD processors per node, given 128 cores per node, usually 256 gig of RAM, but some nodes have 512. And there's actually, it's dual rail, so there's 2 Slingshot interfaces per node to give high bandwidth, low latency communications between all the compute nodes. There's various storage systems, including parallel file systems, which are used for storage during runs, and the Lustre file systems. And there's also a solid state storage, which we're just bringing into service at the moment and starting to test and run with, which is going to be integrated over the next few months. And then the home file system, which is standard NetApp and NFS appliances. And as well as the service technology, which is mostly what we're concerned with here, of course, the service provides a lot of other stuff around the side, around and about, and actually, it's the people that make the service work as well as the technology. And that comprehensive support comes from experts at both EPCC, where I work, and also from HPE, as I've mentioned. We also provide a huge amount of training, which obviously these webinars are part of that training offering, but there's also various courses which are available through the website. We do a lot of that sort of stuff. And there's also support calls, which are known as the ECSE calls, that allow the employ research software engineers or other people to improve code to run on ARCHER2. And there's also a section that's outreach and engagement with the public and the wider research community. For example, we were recently at the Big Bang Fair in Birmingham with a stand that included a lot of stuff about ARCHER2 and about high performance computing, and that was presented to school children. And thankfully, that sort of stuff got up and going again a bit more this year after it not being available during the COVID-19 pandemic. So that's the ARCHER2 service. I'm going to talk a bit about the benchmarks that were chosen and were run here to investigate the performance of UCX versus OFI, and then go on to some results and some summary and conclusions at the end. And there's plenty of time for discussion and questions if people want to ask things. So the full detail, this is a summary of the work. The actual full details of the benchmarks and all the results we produced and the analysis scripts we used to produce the plots you see here, and actually the underlying data is all available online on GitHub in a repository. So if you want to take the results, compare data to things on other systems and things like that, you can go just to the public GitHub repository and find out exactly what we did in terms of job scripts, how we ran it, input decks, output files and things like that. That's all available there online, publicly online. So it includes the description, the input decks, the job submission scripts, build instructions, the versions of software, the raw results and outputs, output from some sort of profiles. We ran on different node counts using the Cray MPICH Lite profiling software and the analysis scripts. In terms of the benchmarks we've run, typically there were 5 runs of each benchmark at each node count, and with different transport protocols and different setups. And the best performing of those 5 was used for the analysis that you're seeing here in this presentation. The actual benchmarks we took were mostly application benchmarks, and were mostly things that were used in the ARCHER2 procurement, with a couple of additions. So the applications of CASTEP, CP2K, GROMACS, and OpenSBLI, they were all part of the original procurement benchmarking set for the ARCHER2 service. And we also added in, did some runs with NEMO, which is node regression modeling code, and VASP as well, which is a material science code that's heavily used on the service. We've also used some synthetic benchmarks, specifically the Ohio State University MPI micro benchmarks, to try and understand some performance differences that we saw with MPI collective operations. The exact same, the slides will be available. Yes, so the recording will be available on GitHub, and the slide deck will be available as well on the ARCHER2 website. after the presentation. So a bit more description about the application benchmarks. Apologies for the overlap with the logo here, part of the conversion of the PowerPoint presentation into Confluent, into this Confluent software means that sometimes the fonts don't quite work as they were originally in the presentation. There's some details here, but broadly what we're trying to say here is give some links to where the benchmarks came from, also say a bit about where the performance limiting routines are in the benchmark. So for CASTEP, especially for this CASTEP benchmark at large node counts, MPI auto or V is typically the routine that limits the scaling. In CP2K, we've seen here it's mostly MPI or reduce coming out of various routines that there's implicated at high scale. GROMACS uses mostly point-to-point MPI communications when it scales out for this benchmark. NEMO has a variety of MPI collective operations that are implicated in its performance as it scales out. OpenSBLI is a grid-based CFD application and uses point-to-point MPI calculations in a sort of regular grid pattern. And VASP, depending on which benchmark you run and which ones and you'll see in a minute from the profiles, it's MPI collective operations, usually MPI auto or V or MPI or reduce, depending on the transport protocol. But we'll discuss those in more detail when we look at the results for the individual benchmarks. In terms of build environment, I'm not going to go in huge amounts of detail. We try to be reasonably consistent in terms of what we are building and the environment we're using. So the system software at the moment on ARCHER2 is Shasta 1.4. We built everything in the Cray environment release, the 2109 CPE release. That has a particular version of Cray MPICH for the MPI and particular versions of OpenFabrics and UCX, which are the transport protocols we're looking at here. In terms of compilers, some of the codes were built with GCC 11.2 and some of them with the Cray compiler environment 12.0.3. And other components we use, such as FFTW and the NEMO benchmark also uses XIRS or, for the I/O output. But we try to be consistent in terms of particularly the transport protocol versions that was used for all the benchmarks, so we're comparing like with like, and we try to be as consistent as we could with compilers and all the libraries. So let's move on to actually the more interesting stuff, which is actually some of the results. And I'm going to go through the application benchmarks one by one in this section, show you a comparison between OFI and UCX for the benchmark, then talk a bit about the profiles we ran, which revealed which routines, which MPI routines in particular, took up most of the time. And then finally talk about some synthetic benchmarks and then try to draw some conclusions at the end of this. So we're going to start with the CASTEP benchmark. I think all of the plots, if I spot one that's different, I will make sure I flag it. These are performance plots. So up on the y-axis is better performance, and the x-axis is typically a number of nodes used for the calculation. As I mentioned at the start, we were interested particularly in scaling out to larger number of nodes. Not all of the benchmarks support scaling out to very large numbers, but some of them did, but we tried to go as far as we could with the benchmarks. So looking at CASTEP here, there's 4 different, and in these CASTEP ones, this was all with 128 cores per node. It was hybrid MPI plus OpenMP, and there's two different distributions of MPI ranks and OpenMP threads here. There was ones with 16 threads per task and ones with 4 threads per task. Okay, so and you can see actually the performance between there's not a huge amount of difference between performance for OFI and UCX for this CASTEP benchmark. Anyway, the major performance difference becomes between using between how many threads you use per MPI task for this benchmark. So at the lower core counts down on the left-hand side of this plot, you can see that you tend to get the best performance when using only 4 threads per task. But as you scale out, it switches over to maybe 16 threads per task, doing better. But very far over on the right here, you can see that nothing's scaling very well. You're beyond the scaling limit of this code anyway. of this benchmark anyway, sorry. So really the scaling limit for this benchmark is 64 nodes here, and we're for 4 threads per task. But it's interesting to go further here because it reveals differences in the performance, or potentially could reveal differences in the performance of the MPI routines for the different transport protocols. But in this case, there isn't any difference. If you look at the 16 thread per task curves here, the dashed line, the solid line, the orange ones, the dashed line is the UCX and the solid line is OFI. So actually the performance is essentially identical between the two transport protocols for this CASTEP benchmark. There's some summary here, but I mean, if you look at the profiles, as you'd expect, where the performance was so similar at different nodes. So there's 2 different node counts here, one where it's in the good scaling regime, 32 nodes, one where it's in the poor scaling regime, 128 nodes, and there's a summary for the OFI profile and for the UCX profile here. But as the performance is very similar, you'd expect the profiles to be very similar too, and that is indeed what you see, right? In the regime where the scaling is still working pretty well, you can see there's about 40% in MPI or 12V and some other time, but about 50, excuse me, about 50% of the time is spent in MPI communications and 50% in calculation. When we're in the regime where the scaling isn't working well, we can see we're over 90% of the time in MPI calculations, which is what you'd expect once you'd gone past the limit of scaling for the benchmark. So essentially, there's not much to see here in terms of difference of the different routing protocols. If we move on to the next benchmark, we do see a larger difference. So this is CP2K, another materials modeling code, but it works in a slightly different way to CASTEP. Uses different algorithms. You can see that the OFI performance is a lot worse than UCX here, even at lower node counts where the scaling was still quite good. In this case, all of them used 8 OpenMP threads per MPI processors, and all 128 cores per node were used for either threads or processes. So in this case, UCX is making a large difference to the performance. And if we come and look at the profiles in a similar way to before, at the lower, well, 64 nodes around, for OFI, 16% spent in MPI, and for UCX, almost 12% spent in MPI. And obviously that increases when we go up to 128 nodes, up to around 20% and 15%. But if you look at the actual routines that are taking up the time for the OFI and UCX, you can see they're actually quite different. So for OFI, all 12V seems to show up in the profiles, whereas that doesn't show up at all in the UCX profiles. So what this means is that there's something in the performance of all 12V for this benchmark, or for these sizes, or for how this code uses all 12V, that's performing much worse using the OFI transport protocol compared to UCX. Now, as you saw from the previous benchmark, the CASTEP benchmark, it was heavily dependent on all 12V, but we didn't see any difference in performance. So there must be some sort of difference in how CP2K is structuring those all 12V calls compared to CASTEP that is actually translating into different performances. So, and I'm not saying that this is a problem with the code or anything like that. What I'm saying is that the calling pattern for all 12V in CP2K must be different in some way from the calling pattern in CASTEP, and then this is translating into performance differences for OFI. So maybe OFI has been particularly well optimized in one type of way of calling it, or for particular data sizes for calling OFI, whereas for another size, UCX more effort maybe has gone into improving performance, or it is just naturally better performing there. So one of the things you'll see in this presentation, I think, is this strangeness around particularly MPI or 12V, and we'll see it later for VASP as well. In that, for some benchmarks, particularly the CASTEP one, the performance looks fine. And for other benchmarks, the performance, the OFI performance in particular, does not look fine in the same way. Okay. So what that means is it can be quite difficult to give coherent advice to users on what to do to get best performance. We move on to GROMACS, which, if you remember, it's a biomolecular simulation code, and most of the communication is dominated by point-to-point type stuff, type communications, and these are, in this case, there's no OpenMP threads at all. It's pure MPI, 428 cores per node. Scales well. This benchmark scales well up to 64 nodes and then stops scaling suddenly. But there's no real difference between the UCX and OFI transport protocol performance here. And that's exactly what we see. If we look, that sort of is what you'd expect then, that the profiles would look very similar between the two codes. And that's not quite what we see in this case, unlike the CASTEP one. So if we look where both of these profiles are from where the code seems to be scaling pretty well, but the profile at the low core count is pretty similar between OFI and UCX. But once we get up to 64 nodes, you can see there is a large difference, right? I mean, in UCX, there's only about 50% of the times in MPI, and for OFI, almost 90% of the time is in MPI. And, a lot of that time is in scatter V, whereas scatter V just doesn't appear at all in the UCX profile. So there's some difference in the performance of particular routines. Excuse me, just a minute. I'm going to... Sorry, there's some difference in the performance in the underlying transport protocols that is manifesting itself in different ways in the profile here. But in this case, as I said, if we look back at the performance curves, it doesn't actually seem to be having a big effect on the differential performance between the two transport protocols anyway. So again, it's reasonably it's a little bit complicated and makes it less clear for us to be able to provide clear advice to users about what actually is going on under the hood here. I'm going to skip through these next ones reasonably quickly. This is NEMO, the ocean modeling code, and you can see actually there's not much performance difference even out to, I mean, it doesn't go out to huge numbers of nodes, this benchmark, but there's not much performance difference between the protocols there. And we struggled to obtain profiles for the NEMO code for reasons we don't quite understand at the moment. OpenSBLI, which is the CFD code, mostly point-to-point communications. Again, not a huge amount of difference between OFI and UCX. Maybe at the highest node counts. These are going out to very large node counts now, to 512 nodes. OFI does seem, UCX does seem to have a bit of a performance gain over OFI. And if we look at that, if we look at the profiles for these ones, they're quite similar between the two transport protocols, as you'd expect if the scaling curves look the same. The MPI parts are here. The MPI parts are really based around point-to-point comms and not critical to the scaling. The weight all calls that you can see here growing in time are actually part of the calculation initialization. And what that means is that when we scale up, the initialization, the calculation takes longer, but the actual runtime is scaling well. And because these benchmarks only run for a short time, then this starts to dominate in the profile. We did some tests by essentially extending out the number of iterations for this benchmark to large numbers, and you can see you can just easily reduce the amount of time spent in MPI and MPI wait all just by extending the length of the simulation. So you're spending more time doing compute rather than calculation initialization. So in a real use case where people will be running for 24 or 48 hours when they're running these types of models or simulations, you'd expect actually the MPI time to come down, and this wait all, this large amount of wait all time is actually an artificial artifact of running for a short amount of time from running a benchmark. So, and finally, we're going to having a look at VASP performance, and this is sort of similar to the CP2K story a bit. It's a pure MPI, no threading. Again, we're using all 128 cores per node for MPI processes, and you can see the UCX version of this benchmark scales much better than the OFI version. And again, it's a similar story to CP2K in that if you look at the actual profiles, especially in the regime where OFI is no longer scaling well, you can see that a large amount of the time ends up in MPI Auto-V for OFI, but that doesn't really appear, isn't manifested in the same way for UCX. So there's something again in MPI Auto-V becomes the dominant routine, so its performance is poor relative compared to the UCX version, as we saw for CP2K. But remember, we didn't see the same for CASTEP, which had a large dependence on MPI Auto-V anyway. So the next step as part of the study, I think, was we thought, well, can we look at MPI Auto-V in particular, because it seems to be particularly implicated in poor performance for at least two of these benchmarks with OFI versus UCX. So we took the synthetic OSU benchmarks and ran with OFI and UCX at a variety of different different data sizes to see if we could spot any sort of difference here. And as you can see from these plots, these are timings this time up, so higher is worse performance for these plots, so they're slightly different from the other ones. These are 4 different message size calculations, one with 4 bytes, one with a kilobyte, one at 32K, and one at 128K. Okay, so not hugely large message sizes, but when we looked, when we tried, but we still can't see any difference between OFI and UCX performance for MPI Auto-V, even at different message sizes. It was harder to run much larger than this, particularly up to large number of nodes, because you just end up running out of memory with these synthetic benchmarks when you try to run very large message sizes at very large node counts. So this isn't actually helping us in understanding where these performance differences with MPI Auto-V are coming from. At least in a simple sense, it was the obvious step to do. So it doesn't really tally with the difference in performance seen for CP2K and VASP, where the reduced OFI scaling performance was linked to slower MPI Auto-V operations. So what this is telling us is we need to go back and do some more detailed analysis. The detailed analysis there, I think, in this case, is to go and look specifically at VASP and CP2K and CASTEP, and try and characterize what the pattern of usage of MPI Auto-V looks like. What are the message sizes? How often are they called? Is there any sort of packing and unpacking at the end? Do all of the MPI processes call MPI Auto-V in all cases, or are they running on some sort of sub-communicators? So actually, say maybe a difference between CASTEP and VASP might be that CASTEP is using a subset of processes for Auto-V, and VASP is using all the processes, leading to this challenge with scaling. So I've already sort of hinted at a few next steps here and where we're going to. So the next step, I think, is to look into the characteristics of MPI Auto-V use in the application benchmarks to understand the performance issues for OFI. And can we distill this down to a synthetic benchmark that demonstrates the issues? And this would then be something we could feed in to the OFI developers, and say that this is what we found. What could be done to improve the performance here, and understand what the differences are between Auto-V and CASTEP and the OSU micro benchmarks compared to CP2K and VASP. Whereas in CASTEP and the OSU, we see similar performance between OFI and UCX. And in CP2K and VASP, we see very different performance characteristics. We'd also like to extend to larger node counts. That probably means finding some different benchmarks and different application benchmarks to understand, how it continues to scale out further. There were some problems with stability of very large node count jobs when these results were generated earlier this year. But over the last few months, a lot of work has gone into fixing those, and large node count jobs are much more stable now. And having this data, we can use it as a baseline for when software is updated. So as the Shasta version of the OS is updated, as the Slingshot software is updated, the MPI libraries and new versions become available, we can retest and see how things change. We haven't had a huge jump in terms of software available on the system since we ran these tests, though there is a newer CPE, so a newer MPI library available for us to repeat the test, which we haven't done yet. But there may be more improvements going further down the line that we need to test out. So Michael's asking, when we ran the OSU Auto V benchmark, how did you vary the message size? So the message size is automatically varied by the benchmark. So when you run the OSU benchmarks, you get reports on the performance for a variety of message sizes. By default, I can't remember what they run between. It's something like 1 byte, 0 or 1 byte up to I think it's more than a megabyte. But as I mentioned, as you increase the number of MPI processes, for larger messages, the memory requirements become quite demanding, and you struggle to use all cores on a node, which you need to do because that's what the applications are doing generally, and still be able to test with larger message sizes. So, in summary here, I mean, the choice of OpenFabrics UCX actually can have a very large effect on application performance, and particularly large effects have been observed for benchmarks that use MPI Auto V convective operations. Typically, I mean, across all of the benchmarks I've shown here, there doesn't seem to be a case where OFI gives better performance than UCX. So I think typically what we'd advise people to do is to try in the first instance with UCX, and if that runs into problems, fall back to OFI. Now that's contrary to how the system's set up, because by default on ARCHER2, you get the OFI transport protocol. So you do have to make an active choice to select UCX by switching out the modules as described in the user guide. For the centrally compiled executables of CP2K and VASP and CASTEP, that change is made for you. So if you're using the centrally installed versions, they will be using UCX rather than OFI. But if you've got your own code compiled, or you're compiling your own versions of those pieces of software, then you will need to at runtime at least manually switch to the UCX version, because OFI is default on the system at the moment. But benchmark, I guess the other point to notice is the benchmarks are around point-to-point MPI routines, so typically grid-based codes that don't do huge amounts of collective operations, show much smaller variation in performance between OFI and UCX, and actually the performance variation is typically within the sort of performance variation you'd expect just for doing different runs, for doing multiple runs at different times on the system anyway. So there doesn't seem to be there's a huge amount to gain if you're using those type of MPI routines in your code. It's typically if you're using collective operations where you can see the difference between OFI and UCX. And I'll put the link there again to the repository that contains all these results. There is some further work that needs to be done to explore a bit more, as I mentioned, and we'll hopefully get a chance to look at that relatively soon. But I think where we started with this was to be able to try and provide some coherent advice to users, a sort of simple advice to users. And actually, the simple advice to users on the system is the best we can get, I think, in some sense, is if you're using, particularly if you're using collective MPI operations in your code, then you should definitely test out UCX and see if it makes a difference to performance over the default OFI. There's always a chance that, I think there's a reasonable chance that it's going to help you out there. And what it means for us when we're compiling central versions of code to make available to users, is that we build in the UCX version rather than the OFI version. So I realize it's a bit of a whirlwind tour through lots of data, but I guess I've been able to draw some quite broad conclusions, I think, here. So I'm happy to take questions and things like that. So Thomas asks, which UCX transports have you used? Have you compared the different UCX transports? So I'm not quite sure what you mean there. There are different options you can provide to UCX in terms of layers and things like that. But which exactly do you mean, Thomas?
Do you hear me?
Yes, I can hear.
Thanks for the talk. There are different UCX transports like RC, UD, or something for CUDA, and have you compared them?
No, we haven't gone into any more detail with that. We're taking the default as it's set up on ARCHER2 at the moment by the program environment, and I'd actually have to go and look more closely to check exactly which one of those it was choosing by default. So that is interesting. We hadn't moved on to looking at that sort of stuff. So I have been on a different system investigating those things for the Rockport interconnect, which can also use UCX and then to use the different transport ways. So we should bring some of that back. That's a good idea, a good point.
Okay. Yep.
So Ning's asking, would you say the performance differences are specific to the slingshot interconnect? So I think I would be not very confident in taking these lessons and generalizing them to different interconnect types. Okay, because the way slingshot works is quite different, say, from InfiniBand interconnect and things like that. Now, there may be more commonality between slingshot, or there may be lessons that can be taken more closely between slingshot and other RDMA converged Ethernet solutions like Rockport and things like this. But we haven't looked at that. So, I think if you've got a different interconnect type, I think testing and testing yourself is probably the right way to do it. Like I just mentioned previously, at the moment I'm testing, doing some tests on a Rockport-based system, and we will try and compare between the two. But the challenge a bit is that most of the benchmarks we ran here on ARCHER2, because we were interested particularly in large scale and high node counts, most of the other systems you get access to, these sort of technologies have much lower node counts. So it can be difficult to replicate these tests, and that maybe these benchmarks aren't suitable for running at smaller node counts. And because almost what you want to do in some sense with these types of tests on the interconnect is go beyond the good scaling point in the code, because that sort of amplifies the problems a bit, so you can see the differences more clearly. And when you're on smaller node counts, you probably need smaller or different benchmarks to be able to push out of the scaling regime and amplify the effect, to try and help you understand the trends. So taking these specific benchmarks, if you've got a big enough system and running them on the system, great. But for smaller systems, you typically need a different set of benchmarks to be able to run. And like I say, when you get previews of different technologies, it's often on a smaller system than something like ARCHER2. So I think potentially comparisons between other Ethernet-based interconnects may be useful, and maybe general lessons that can be taken. But I think I'd be much more wary of taking the lessons between an Ethernet-based solution like the slingshot over something like InfiniBand. Yeah, so why is VASP showing all-to-all calls with UCX but not with OFI? So with all-to-all calls with UCX but not with OFI. Okay, let me skip back to that. Yeah, okay, so why is it show? So you can see here, particularly in both cases, all-to-all is showing up in the UCX profile, but isn't showing up in the OFI profile, right? Whereas that sort of says, the logic I sort of spoke through the presentation, that means that all-to-all is maybe poorer performing on UCX than it is on OFI. But I don't think that's quite the right conclusion here. I think because so the difference between the profiles is that, especially when we're in this regime where it's not scaling well, particularly for OFI, is that so much time is being taken in auto V that it's swamping the profiler a bit, right? Because the profiler decides at what threshold to show you what routines spending time in. With so much time in auto V, there's this huge peak of time in there, and that swamps what's available. Whereas for UCX, because the profile is a lot flatter, you're just seeing a much more variety of routines. These are essentially sampling profiles. So what it's doing is at every time interval, it's saying which routine am I in, which routine am I in, which routine am I in, and when the time is weighted so heavily towards this routine, the chances of you hitting a routine where less time is spent become less, because you're statistically more likely to hit this routine. So I think it's mostly just a statistical effect. Sorry, I was struggling to say that word because it's a sampling experiment and not a tracing experiment. So exactly. So that's one of the things we want to look at. I'd have to. So what we need to do. So the Cray EPCC Lite gives you useful overview statistics on the usage, and is easy to run and easy to do. But as I said, we need to do some more detailed investigation. That probably means doing some tracing experiments, which will give us access to the message sizes for the different application benchmarks, which we can then go and look at and see if we can generate a synthetic, have a look and see if we can match them up with the synthetic benchmarks. With the OSU benchmarks, we tried to pick a variety of sizes that would run across up to a reasonable number of nodes, but obviously, to see if we could just see some effect there that we could then work backwards from. So this was very much a sort of first pass of things we could do relatively easy to investigate. But as I mentioned, I think what we actually need to do now is take a step back, do some more detailed profiling of the applications, understand something a bit more about the profile of the MPI calls that they're making, and then go from there. Yeah, okay, so so we went up to 500 nodes here for the OpenSBLI benchmark, and that wasn't because of a scaling limit of that benchmark. That was because at the time when we were doing this analysis earlier in the year, there were stability issues with large jobs. My experience since some fixes went through maybe a month or 2 months ago, or some improvements went through to the stability of the nodes and the stability of the interconnect, is that I'm consistently able to get 2048 node jobs launching with no problems whatsoever. I've done some tests up to just over 4,000 nodes as well, and had success with those, though I haven't tried it often enough to be able to say with any sort of confidence that you'll get a good what the proportion of those size jobs you'll get launching and working. Well, as you say, you've seen various issues getting jobs to launch on 2,500 nodes or more. What I have seen, at least I haven't tested it particularly recently, and maybe I should go and have a look again, is that when you get to very large node counts, then I have more problems launching with UCX than I do with OFI for the benchmarks that scale that high. To that scale. So with OFI, I could tend to be able to get consistently very large jobs to launch. Well, this is my anecdotal experience anyway. Whereas UCX, I see more problems with initializing the MPI communications once you get to very large nodes. And of course, then you end up with this situation where UCX typically has better performance, but it can be more problematic to get the jobs to launch. OFI has worse performance, but I can get more stability at large getting the jobs launched at large node counts. But I think we need to do some more. Potentially, we are looking at stability of reasonably large jobs, but we need to maybe put in some tests for launching very large jobs as well and revisit that, both with UCX and OFI. Yeah, and that's the other problem with OFI, right? It can be very slow to do the initialization of the MPI setup step, whereas UCX seems to be better at that. But a large node counts, I don't know, that something happens, it runs out of shared memory or some such thing. It seems to be what happens. It seems to be what happens on very large node counts. Well, I think this is one of the challenges we have here, is that there's a lot of things to potentially look at, and time, there's only finite time to look at them. So there's lots of different ways we could take this in terms of looking at the comparison of OFI to UCX in terms of scaling the performance and what particular MPI routines like MPI auto or V are doing. But also there's these initialization questions for very large jobs, which are the most stable, and what's the advice for using OFI UCX there, and because once you get up to that scale, there are various environment variables that affect the initialization performance of OFI, I know, and possibly UCX as well, which are probably not very hugely well tested, right? Because there's not that many people that have run, well, whatever, 2048 times 128 MPI ranks. There's not many systems around the world where that could be tested out. ARCHER2 is one of the few of them. So those bits of the transport protocols of both OFI and UCX are not well tested, right? So we're pushing into things and edge cases that haven't been well explored by the developers of those libraries. So we've got just over 5 minutes left. So if anybody's got any last questions, that's fine. If people need to leave and get out, sorry. Stan says, you said that the Frontier network was not quite the same. How is it different? Okay, so Frontier is Slingshot 11, not Slingshot 10. The difference, or the main difference, is that the network interface cards in the compute nodes for Slingshot 10, which is what ARCHER2 has, network interface cards are Mellanox cards with the Slingshot switches in the system. For Slingshot 11, they are Slingshot network interface cards in the nodes with the Slingshot switches that connect them together. So they have a slightly different feature set. I think also it may mean that UCX is not supported in Slingshot 11. Though I don't know if there's anybody from HPE on the call who knows the answer to that. That one, we don't have a Slingshot 11 system, so I've not really played, and I've not had access to Frontier to test. But I think because it's not Mellanox technology, yeah, there's Douglas. Thanks, Douglas. Yes, there's no UCX on Slingshot 11, and that's because the network interface cards on the nodes are not Mellanox cards. I think it's OFI. Douglas might be able to confirm, but my understanding was that it was OFI. And this is why OFI is the default within the Archer, because that's actually the sort of officially supported HPE stack. Okay, I'm happy to answer any more questions people have, but I just wanted to, as people are heading off now, and say thank you for coming along and for your questions. They're interesting, and like I say, there's a lot more investigation to be done here, and a lot more things that could be taken forward. So yeah, I hope you find it at least interesting, potentially useful, and yeah, thank you for coming along.